Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to be kind of an introductory video into the concept of AC voltage and AC current. So let me talk about what I've got drawn out here. We're going to take a look at this picture right here, and what we're looking at is, imagine this current loop here. It's got some sort of area to it that we could calculate. We're going to say it's got maybe n loops here. You know, maybe there's 5 loops, 10 loops, 100 loops, that doesn't matter. Imagine that it is free to rotate about this axis, and it is immersed in a uniform magnetic field that points to the right. Now, if we want to get this thing to start rotating, we're going to have to apply a mechanical type of input here, a torque. So imagine that we apply a torque in the direction shown, and that's going to make this thing, start rotating basically. Now, we're going to take a look at this from a top view, and here's what we would see over to the right here. Here's the top of this current loop. That's this guy right here. And the normal vector would point roughly like this. Remember that the normal is a vector that is perpendicular to the area of the loop. Right? And this is just a unit vector here. It's just keeping track of a direction for me. Now, there is some angle now, theta, between the magnetic field vector and the normal. And magnetic flux is a very important concept for thinking about voltage here. Remember that magnetic flux is magnetic field strength times area times the cosine of the angle between the magnetic field vector and the normal. The cosine part basically does this. It takes the component of the magnetic field in the direction of the normal and then times the area. So if we were to make a graph of the magnetic flux against time, keep in mind that it's equal to field strength times area times cosine theta. Now this is per loop here, so if you don't mind, what I'm going to do is I'm going to put an n in front of this for n loops. And then the theta can be expressed as the angular velocity times time. So if I go back and think about this thing rotating at an angular velocity, which is rate that theta changes, so average angular velocity is change in theta over change in time, or in the language of calculus, we could talk about instantaneous angular velocity, which is d theta dt. This would be measured in radians per second. So this function would describe the magnetic flux, and that function is going to look something like this. And I think what I'll do here is let's put a minus sign in front of it here, just to make my math function here fit this graph that I drew. All right, where this starts is not important. See, magnetic flux, when we take a look at this, as this thing rotates around, we've got this surface right here, and now it's in this orientation, and now it's in this orientation. Now, notice I'm actually talking about like a side of this. Which orientation gives a positive magnetic flux is completely arbitrary. So this graph really can arbitrarily start here or here. It doesn't matter at all. I made it start here because I drew my voltage function like this, and I wanted to make these match. So this minus sign not important for the discussion. So Faraday's law of induction basically says that the induced voltage is equal to the time rate of change in magnetic flux. It's actually equal to minus the time rate of change in magnetic flux. We're not going to need the minus sign here. I'm just going to absolute value this and not worry about that sign. And if I go through and time differentiate this function, we're going to get the following expression here. Let's see, magnitude of the induced voltage is equal to, now this stuff's all a constant, and again, I'm going to throw the minus sign out. I don't need it. NBA derivative of cosine theta is sine minus sine theta times the derivative of the inside function. And I'm going to put that out in front. And again, I've tossed the minus signs. Or if you want to think of the minus and the minus as being plus, that's fine. It doesn't matter. Right now, we really only need to think about magnitudes. So I get this expression looks like this. You notice it's sinusoidal. So here's an expression for the voltage induced in this current loop. This guy right here is a constant, and if you work the units out, that constant will come out to volts, and you notice it's sitting in front of the sine wave here. So this represents the maximum voltage that we're going to get in this current loop as it rotates. And if I graph this function, Here I've got a quick sketch of it here. The induced voltage, again, it's a sinusoidal graph. It's looking something like this. Right? Now you'll notice that the voltage, half the time it's in one direction, half the time it's in the other direction. This is what's referred to as an AC voltage. The AC standing for alternating current. And you'll notice that it's sinusoidal. It has a certain frequency. The frequency is the number of cycles per second. It has a period. I usually just put big T for period, which is the time to complete one cycle. The relationship between the period and the frequency, well, is an inverse relationship. Or I should say a reciprocal relationship. The frequency is 1 over the period. This is how we go back and forth between period and frequency. Okay. And it also has what's called an angular frequency, the number right in here. I'll put that over here. The omega is called the angular frequency. And that's related to the period and the frequency on the graph. So the next part of this video, I'm going to talk specifically about the United States power grid, right, the U.S. power grid. And I don't really need this stuff anymore. I'm going to go ahead and get rid of this now. Oops. All right, so the U.S. power grid. USA. All right, so the power grid is an AC power grid. I'm going to do a quick sketch here of voltage against time. It's sinusoidal in nature. Oops, I'm going to put that a little higher. Now, you know, actually starting at 0, 0 is not important. AC circuit problems, almost always you're talking about averages over time, so it's not important that this actually start at 0, 0, but I always draw it like this and then represent it with a function that looks like V equals some sort of V max sine of omega t, omega being the angular frequency. The U.S. power grid, the maximum voltage is 170 volts. So on this graph, we'd be getting as high as plus 170 and down here to minus 170. Now, a wall outlet, if you take a look at a wall outlet, you know, they kind of look like this. You got these guys here and here, and I'm going to blow one of these up. They typically look like this. You've got an opening there, a smaller one on the right, and this kind of semi-round looking thing. All right. What's referred to as the live part of this is this guy right here. That's the one that this voltage applies to. This is where the electrical voltage is driven from, or the power of the circuit comes from. All right. This guy right here is the neutral line. This completes the circuit. This one right here is just a ground. And again, what I love about the term ground, you can't mean it more literally. This thing, if you follow the wires all the way, you know, through the building, through the circuit breaker embed, this is eventually connected to usually an 8 or maybe 12-foot copper rod, or maybe sometimes aluminum rod that's driven into the earth. So this one's for safety. This one's driving the circuit. This one's completing the circuit. Let me talk about the plus 170, minus 170. So there's, you know, these negative numbers on voltages, I think, tend to confuse people. They make them think that there's something that they're not. It's just about direction. Half the time the voltage is pushing current basically at you in this picture, and half the time the voltage is pulling current away from you in this picture. Which one is plus and minus is completely irrelevant. You could define outward as positive or inward as positive. All right, so this minus, this is just about direction. So like in this part of the graph, perhaps the voltage is trying to push current at you here. Then in this part of the graph, the voltage is trying to push current away from you. But you know, you could completely reverse that if you want and say that, okay, in this part of the graph the voltage is trying to pull current away from you, and in this part of the graph it's trying to push current towards you. All right. The frequency of the US power grid is 60 Hertz. And remember that period and frequency, they have a reciprocal relationship. So the period here is 1/60th of a second. And that means in this picture, the time from here to here is 1/60th of a second. Okay. So this video is starting to get a little bit long here. I'm going to finish it by chatting a little bit about the voltage in this 170 volts. And if you're watching this video, this right here may not be familiar to you. You're probably sitting here going, this voltage is 170 volts? I've never heard of that. When I buy a light bulb, it doesn't say 170. It says typically something like 120 volts, or sometimes they say 110 volts. So what's up with that? Well, I'm going to save that for another video, for my next video in this series, but for now I'll just say this. This is an average voltage. The 170 is the peak on the curve, how high this gets, here, 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 and so forth. And 120 volts is the average. Now it's what's called a RMS value, and because I'm at 11 minutes here, I'll save that for another video. So the real important points, the AC power grid of the United States is a sinusoidal power grid. Has a peak of 170 volts, frequency is 60 hertz, period of 1/60th of a second. Now you notice I keep saying in the United States. So other countries also use sinusoidal AC power grids. Europe uses a sine wave. However, their peak is much higher and their frequency is slightly different. I haven't been to Europe and I haven't looked this up recently, but I think in Europe they use a power grid that this might be 220 or 240 or something like that, and the frequency is slightly different. I believe it might be 50 hertz. So if you go to Europe, don't plug your phone in without using or don't plug your charger or any of your electronics in without using some sort of adapter or converter. So anyway, I hope that this video gives you a reasonable idea of what AC power is. Second video in this series will describe the relationship between the 120 and the 170. Have a great day.